The second review lesson that we are going to do is related to functions and transformations, as this is a huge component of the advanced functions course. Briefly, we're going to go over some definitions. So you'll recall that a relation truly is any relationship between two variables. Throughout your high school career, you've seen several relations, y equals mx plus b, quadratic relations, trigonometric relations, exponential relations, lots of good stuff there. You were also exposed in grade 11 to the domain and range. Recall that the domain is the horizontal span of x values that are covered by a function. So you could just say that this is the x values covered by the function. And range is side to side, so it's the horizontal span of how things are going. We can write, or sorry, domain is the horizontal span of how things are going. Versus range is the vertical span. So these are all of the y values that are covered by the function. And so this is how far up and down does the entire function go. This is vertical, while domain is horizontal. And we write these using two different types of notation. We can use standard notation, and we can also use set notation. In standard notation, it's right like this. I'll write it a different color. Curly bracket. Domain, we are talking about x, so I'm going to use x is an element of all real numbers, and that's where you put in your condition. Don't forget your such that. Versus range, we would do curly bracket, y is an element of all real numbers such that ... And again, you'd put your condition. Just a quick zoom in here. These e's, the element e's, they look like a C, just with a line drawn through, okay? And then range, or sorry, R for real numbers, I've drawn the capital R, and then I've made it a bar to indicate that this is not actually a variable, but it is indeed a set of numbers. That's with standard notation. You perhaps might also be familiar with set notation, which is using brackets, and that's where you have either curved or perhaps square brackets, or a mix of both, two numbers and a comma in between. Last but not least, the term function is really important. Function is distinguished from relation because for every input, there is only ever one output. And you can check this primarily with functions using the vertical line test. Recall that the vertical line test basically is you draw a vertical line anywhere on your graph, and if it hits the function or the relation more than once, then you do not have a function. So let's get an example here. Determine if the following are functions, and then state the domain and range. So let's take a look at our first graph, which is purely a series of points. The question we have to ask ourselves is there anywhere along the span of this graph where I could draw a vertical line and it would hit the graph twice? And here my graph is only comprised of a couple of points. We can see at the end the answer is yes. I could draw a vertical line right here along the value x is equal to 1, and I would hit 2 points. I would hit the point 1, -1, and I would also hit the point 1, 3. So this fails the vertical line test. Okay. If I were to write the domain for this, my recall domain is the x values, so I would write x is an element of all real numbers such that, And here, because it's just dots, there's only certain values that it can be. So I'm literally going to write x equals. X can be -3. X can be -1. Or x can be 1. My range will set up the same way. Y is an element of all real numbers such that, and again, what are the Y options here? Well, we've got a 4, a 3, a 2, and a -1. So I'm going to write 4, 3, 2, -1. The order doesn't really matter. All that matters is you have them listed. Let's look at our second graph here. Our second graph is an example of a radical graph, if you are not familiar with it. So this is something that looks like that, except just with some transformations applied to it. The question being, is this a function? And the answer is yes, because nowhere along this graph can I draw a vertical line that hits it twice. So it is a function. Yay! We're going to write now our domain and our range, and just to change it up, let's do it in set notation instead. My domain, it starts at -2. My graph doesn't go any further to the left than -2, and it does indeed hit -2, which means that I'm going to use a square bracket with my -2. And then moving to the right, you can see this graph is just going to go on forever and ever and ever and ever and ever. So we're going to use infinity for our right bound, and infinity is not a number that you can touch, so we use a curved bracket. For our range, the lowest that we can go, coming from the negatives, well, this graph is going to go on forever this way, which includes a downward element. So it's eventually, you can imagine, if you were to zoom out, is going as far down as -infinity, which once again is not a number that we can touch. We can just get really, really close. Our upper bound, though, we can see that this graph stops at the number 1, and it does indeed hit 1. So I will use a square bracket there. If you needed to write this as or in standard notation instead, I'll just do the domain so you can see when we're working with infinity here. I do my curly bracket. X is an element of all real numbers. And because -2 is the lowest that it can go, I'm actually just going to write the following. I'm going to say, well, X is always going to be greater than or equal to -2. There would be no other bound on that. It's just greater than. That's for our radical function. Okay, and last but not least, let's do our third graph here. This is an example of a reciprocal function, in case you have forgotten. We cannot draw a vertical line that hits the graph twice, so it passes. It is a function. Now, we have a couple of features of this graph here that are a little bit hidden. I'm just going to add some arrows that were cut off. We have these two sort of imaginary lines that you may recall from last year. We have a vertical one here at x is equal to -2. That is your vertical asymptote. Recall that asymptotes are these sort of imaginary lines that help us to guide when we are sketching our graphs. And our actual function is going to get really, really, really close, but it's never actually going to touch. So we have one there at -2. Horizontally, x equals -2, and we also have one vertically over here at -5, at y is equal to -5. Those are the two asymptotes that we have. So we're going to write here using our standard notation, a little bit easier to represent. For my domain, x is an element of all real numbers such that, and I think we can see that it's going to go all the way to the left, all the way to negative infinity. And on this graph, it's going to go all the way to the right, to positive infinity. So truly, the only number it is never going to touch, that it's going to get really, really, really close to from the left, and really, really, really close to from the right, is -2. So we can simplify that, and we can just say x is not going to equal -2. It's going to be everything else but -2. Let's do that with our range. Similar style. Y is an element of all real numbers such that the only thing that y is not going to touch is -5, because it's going to go all the way up to positive infinity over here, all the way down to negative infinity. And the only thing we get really, really, really close to is that asymptote. Okay, we've established what are functions, we practiced some domain and range, we've reviewed some key vocabulary. Let's talk about graphing now, because about 40 to 50% of this course purely is graphing. Y equals mx plus b, your favorites from grade 9. Or, as we got fancy here, we wrote them as f of x instead of y. Recall that when you're graphing your linear functions, you need to use both your slope and your y-intercept. Here, f of x is equal to 2 over 3x minus 6. Our slope, m, 2 over 3, meaning I rise by 2 and I run by 3. My b value, which was my starting point, is -6, and so it looks like this. I start by plotting at -6, and then I use my slope to plot a couple of other additional points. I go up by 2, across by 3, put a dot. Up by 2, across by 3, put a dot. And I can continue going until I feel comfortable drawing a line. For me, that's 3 points, but you might be a little bit more. Oh, let's try that again. There we go, that looks better. Yeah, for the most part, we get it. That is your linear relation. I've added arrows on the end to indicate that it continues going upwards towards infinity and downwards towards negative infinity. Next up, we have our quadratic function. Here we have it written in vertex form so that we are easily able to identify the vertex. The vertex, as you'll recall, is located, the x value is in the bracket, and it is the opposite. So the bracket says -2, but when we actually graph it, it's +2. And then the y value of our vertex is the number that's sort of hanging out at the end of the equation. In this case, it's +4. So our vertex is located at 2, 4, and I'm just going to go ahead and plot that so we know where we're headed. And then next we have the step pattern that we are going to use. And if you are not familiar with the step pattern, just give that a quick Google, go through YouTube. It's a great hack to sketching your vertex forms of your quadratic functions. I mean, you don't really need it for this course, but interesting to know. Basically, what our step pattern tells us is usually in order to draw the next points, we go down by 1, and then we go down by 3, and then we go down by 5. What we need to do is we need to change our step pattern to reflect the a value on our equation. In this case, our a value is -2. So I need to multiply this by -2 to get our actual step pattern. 1 times -2 is -2, 3 times -2 is -6, and then 5 times -2 is -10. So, how am I going to apply this? I'm going to take from my vertex, I start here, and I'm going to go to the right by 1, and now I'm going to go down by 2, because that is the first number on my step pattern, and I'm going to make a point. Then I'm going to go to the right by 1 again, and I'm going to make this time down by 6. 1, 2, 3, 4, 5, 6. And I'm going to make a point because that's where my next dot is. And I have run out of graph paper space, otherwise I would continue and I would go down by 10 for our next point. And you can sort of see the pattern here if you wanted to continue doing it. So I've got the right hand side of my parabola. We recall that parabolas are symmetrical, so it's super easy to draw the next couple of points on the left hand side because it's just a mirror reflection of one another. So nice. And here's where we all do our best to draw a nice curved line. No promises. Let's see how things go for me. Not bad. And I've included some arrows there to indicate that my parabola does indeed go on for infinity. Let's make that bigger. There we go. In the downwards direction here. All I ask when you're sketching your parabolas is that you attempt to make some kind of curve. As long as it's not a straight up V or a triangle, then that's cool with me. And that's it. We've got our quadratic function there. Next we are going to, there's a quick typo here, we're just going to change this guy to say reciprocal functions. Reciprocal functions are very similar to, or how we graph reciprocal functions is super similar to how we graph quadratic functions using the step pattern, but it's just organized a little bit differently because it's reciprocal. Our first challenge here, unfortunately, lies with the fact that the sort of starting point, recall that reciprocal functions look like this somehow, so we need a starting point. Our starting point is currently hidden. The starting point, we need that to come from the inside of this radical, and in fact it's going to be this number right here. But first we need to factor out this 1 over 2, because the 1 over 2 is going to tell us our horizontal transformation, our horizontal stretch. And we need to know what that actual number is, because currently the 1 over 2 hasn't been applied to it. So let's go ahead and factor that out. It stays under the radical. And you can see where we've landed. It's actually landed at -4. So -4 is going to be our starting point. Sorry, +4, because remember it's always the opposite when it's on the inside. And the second number comes right at the end, just like with a quadratic. So our starting point here is at the point 4, -5, and I can just draw that baby right on my graph. And then you'll recall, remember that step pattern from before where we had, the pattern was you go to the right by 1, up by 1, right by 1, up by 3, right by 1, up by 5. That's what it was for the quadratic. And recall that this is just the reciprocal function is sort of like the inverse, or it is the inverse, I should say, of a quadratic. So all we do is we just swap this. And so here, I'm just literally going to change my arrows. I'm going to say, well, here we go up by 1 to the right by 1, up by 1 to the right by 3, up by 1 to the right by 5. Super convenient. However, we've got a couple of transformations that have been applied here that we need to follow. The first transformation is our 2. It's our A value, just like before. The 2 is going to affect our vertical motion. It's a vertical stretch, and so in this case, it's going to affect our upward. So we need to multiply all of these by 2. So we're actually going to be going up by 2 with every step. And then the second thing that we need to consider is we need to consider this half. This is a horizontal stretch. Recall that it is the opposite when it is inside the bracket. So even though it looks like a fraction, it is a stretch because we need to divide. by the fraction. And every time we divide by the fraction, it's like multiplying by the inverse. So I'm actually going to be multiplying everything by 2. Divide by a half or multiply it by 2. So instead of going to the right by 1, I'm going to go to the right by 2, and then to the right by 6, and then to the right by 10. And you're going to see how quickly I run out of space here. Let's go. I start at my starting point. I've already put that on there. It's at 4, -5. Now I go to up by 2, to the right by 2. I'm going to put a dot right on there. Then I'm going to go up by 2, and I need to go to the right by 6. 2, 3, 4, 5, which is just off the graph for me. I'm going to do my best. I'm going to put a dot right there. And if I could, I would continue along my pathway. Now let's go ahead and connect the dots into an attempt at a nice smooth radical curve. And recall that radicals only go on towards infinity in one direction. It does not go on towards infinity down, because they are the inverse of a quadratic. So actually its sister graph looks like this. So it does not go down forever. And that's your reciprocal. Or sorry, that's your radical. That is not your reciprocal. That is your radical. Try that again. Okay, the next one we've got for you is your exponential. Man, I messed up all the names here. Your exponential function. For this, we're going to use a couple of different pieces. We're going to use our asymptotes, our y-intercept, and a couple of key points. The first thing that we're going to use is our asymptote, and recall that the asymptote is just going to be the value that is sort of tagged on to the end here. And it is a horizontal asymptote located at y is equal to -5. Now pay attention to how I'm drawing this on the graph. Remember that asymptotes are guiding lines. They are not actually a part of your function. So do not draw it as a straight line. You must draw it as a dashed line. Just like that. Okay? And now, literally, to make my life easy, truthfully, all you need with exponential functions is you need 3 points in order to graph. So I'm going to create a little table of values here that I can use to find some of the key pieces of information. I'm going to strategically use when x is -1, when x is 0, and when x is 1. Because recall that when x is 0, you're working with your y-intercept there. And literally all I'm going to do is I'm going to substitute these numbers into my equation and determine what my function is going to be equal to. So when x is equal to -1, I sub it in. I go 2 times 2 to the power of -1 minus 5. 2 to the power of -1 is like saying a half. And so we have 2 times a half is just 1. 1 take away 5 is -4. Now we do it again, this time with 0. So 2 to the power of 0, take away 5. You remember that anything to the power of 0 is just 1. So this is a 1, and we go 2 times 1 is 2. 2 take away 5 is -3. And for our last one here, I'll go 2 times 2 to the power of 1, take away 5. 2 to the power of 1 is 2. 2 times 2 is 4. 4 take away 5 is -1. So I have my 3 points that I can plot. The first is when x is equal to -1. F of x is -4, so I have a point right here. Then I have the point 0, -3. And last but not least, I have the point 1, -1. We can clearly see the curve of this exponential function. We can see it's going to go up to the right, and it's going to span a little bit more horizontally to the left. So I'm going to draw this guy as best as I can, and I'm going to draw it backwards. But really, your goal here is that you're showing that it is a curve. I sort of ended up on a little bit of an angle there, but we get the idea. And it continues infinitely on in both directions. Alrighty, our last function here before we are done with this lesson. Reciprocal functions, okay? We are going to be using both asymptotes, our horizontal asymptote and our vertical asymptote. And we are just going to be using 2 key points in order to help us graph, or really just one if you want. First and foremost, our asymptotes. We find our horizontal asymptote very similarly to how we found our vertical or our horizontal asymptote for exponential function, and it was at this point tagging along at the end there. So we know that y cannot equal -3, and I'm going to draw that guy in as a horizontal asymptote right here. Again, dashed lines. We also know that our denominator for this function can never equal 0. So we know that x can never be equal to -1, because if it is equal to -1, then the denominator is 0 and we've broken maths. We can't do that. X cannot be equal to -1, so I'm going to draw that guy here as a vertical asymptote over here. And we know that our function is going to be located in 2 different quadrants here. It's just a matter of figuring out which ones. I'm going to create a table of values here, an x and an f of x. And I'm going to sub in something nice and easy. I'm going to sub in when x is equal to 0. Let's figure out where my function is located at. Here I'm going to have 2 divided by 1, because 0 plus 1 is 1. So 2 divided by 1 is 2. Take away 3 is -1. So when x is 0, my f of x is equal to -1, which is over here. So that's going to suggest that I have a curve that way, right here. So the super easy thing about reciprocal functions is that they are symmetrical. And so we can actually use this like little hack here. You see how the horizontal and vertical asymptotes, they sort of meet up right here. And that one key point we found was 2 up and 1 to the right. We know it has to be symmetrical, so we can actually go 2 down and 1 to the left. And that'll give us another key point on our reciprocal function here. So we can actually, you can just write that out. You can just put it automatically on there. It doesn't really matter to me. And let's create our graph. Headed in that direction. So we've got 2 key points. We've included our asymptotes, and this is as good of a sketch as it is going to get. Alrighty. So we've covered the 5 favorite functions that you should be coming into this course familiar with. We are going to build on all of them, and that is it for your review today.